Hello everyone, welcome back for this new video. So today we are starting back from the previous video as usual, and for this time, we do have the same configuration. So last video we have been working on the interrupt from the GPIO perspective, and we put this push button, and each time we push this button, so we do have this interrupt indicator that we added for this LED, so the red one, and at the same time we have this blinking other LED. So each time we push it, we should stop or come back to our previous scenario or this scenario. So if I click again, so this is generated, the push button is generated by an external interrupt and not inside the loop of the program, which is quite saving time and more efficient from programming perspective. Great. But here there is still a variable that we don't control, or we're randomly putting, is the delay function that we have been using so far. So for today's video, we will work on the timer that will be used to generate a very accurate, to a certain extent of course, a delay function, where we will be using a timer related to the ARM microcontroller. So this timer is called Systick, and so for this Systick, ARM is directly connected to the ARM microprocessor, which means that whatever the microcontroller having the ARM microprocessor, you would find this Systick timer inside it, and even the register structure is not even different. Even you change the microcontroller, the for the Texas instrument or NXP, if they are using the ARM microcontroller, which is within from M1 to M7, you will find the Systick timer. Great. So the Systick timer is a timer connected directly to the clock of the microcontroller. So the first step to start here, we need to understand what is the speed that my microcontroller is going on. So what is the speed of my clock? Actually, the good thing with Kale, you can easily find this one. So let me first go here. Always check about your clock, which clock are you using. So for the STM32F1 that I'm using, I have a 8 megahertz clock, and let me go to the simulator mode. Okay, good. So after that, let's go for the debugging. Great. And run my program. Inside that, if I go to peripherals and I go to power, reset and control, and open this window, so you will find a lot of details here about the speed of the microcontroller and what I have to look for. So this is my oscillator, which is 8 megahertz, and my final speed after going through PLL is 72 megahertz. So 72 megahertz, if I translate it in second, it means I have 72 million clock cycle in 1 second. Great. So to get 1 second, the clock is going 72 million times. Fantastic. Good. So now that I know what is the clock of my speed, I can go and understand the Systick microcontroller. Okay, to find about this Systick register, this time I'm not using the reference manual, but another one, as this is more about the Cortex M4 MCU itself. So there is a short description here. Let me look for probably, yeah, Systick timer here. Great. So the Systick timer is, as we said, the register which is connected to the microprocessor, the ARM one, and it has 4 registers. We are going to ignore the calibration register, but focus on the control register, on the load register, and the value register. So let's quickly go on it. In the control register, we do have the count flag, this one, and so for this one it goes to 1 when it reaches the counter reaches 0. And then for the clock source, this one is about which source are we using. Is it the AHP divided by 8 or the AHP itself? Finally, the tick int, this is related to the interrupt getting from the Systick. This will not be the topic of this video, but we will look on it for the next one. And lastly, the enable counter register. This is the one that allow the Systick register to start the counting. Good. And the next one is the Systick reload value. So the value here goes, we have 1, 2, 3 bytes. So we can go to 3 byte register. I'm not sure how much the value, but that's 00FFFFFF. Let me take a look and find converter. That's a good converter. So if we take FFF, we said so it's a 3 byte, so it's a 12. Okay, 1, 2, 3, 4. It's quite a huge number already. Okay, and another 1, 2, 3, 4. So that's the number that we can reach. So it's quite a huge number, and it can go to a few days of counting. Great. And this is a register that goes from the top to the lowest number. So if you put 100, it will go to 99, 98 to 0. So if you need to have a 100 cycle, you have to put 99. Good. Next. And this is the final register. This is the current value you would like to put for this, and here where the register will start going to the current value. So to get more on this register, better to go directly more for applications and putting the function. Okay, just before we go back, let me go back again. So we will create the first function, which will be the init function. The init function will be based on this register, where we'll set up this register to the counting value that we need, and then we will create one function which will generate a delay of 1 millisecond, and finally we will create a function which count how many milliseconds we are going to run. Good. So let's start with the first one. So let's close the debug mode, and let's go here. The first one, the void, let's call it a Systick init. Okay, and okay, it's not a void, apologies. This is actually it's a void, sorry. And here also it's a void, as we don't need any data. And then we will start with the first registers. As we are using now the library, this STM32F1, and even we use other libraries for the F4 or F7, it will be same. So Systick, yes, and then now Systick, and we immediately find, and as we said, the first one is the control. So to start working with the Systick register, first we have to set up everything to 0. Okay, and after that we set up the Systick, the load one to the maximum value. So 0x, let's put it as a init 0x00, and then ff. After that, FF. I hope I'm correct. Let me check. So we do have 00FF and 00 like this. Good. So now that we set up this, we put our Systick the Systick of the value here equal to 0 to initiate to 0 our Systick. Great. Okay, so the first step was we put it the control. Let me bring back this one here. Let me close and make this smaller. Maybe we can close it. We don't. So the first thing, we set up all this register to 0, so we can start updating the load and the value. So by putting all this in 0, this is an inactivated register. So after that, we put the value, the maximum value for my load, to how much I'm going, and finally I put the value to 0. What does mean 0? So it will be always going to 0, 0, 0, 0. So there's nothing changed. Great. So as a last step now, we need to put to enable our Systick register, and also go also to this bit number 2, which is the clock source, and we put it as the HB, which means we are getting our pulse directly, same as the microprocessor, and the same clock, and it will be 72 megahertz. Here again, Systick control, and we force a 5. We don't put equal parallel, we really force the 5 here. Okay, so now we had set up this function to initialize our Systick. So let me come here and put the function for the Systick and initialize my Systick at the beginning before starting my loop. Here, so I have the Systick ready. Great. So now we initialized the Systick. The next thing is to count, or to make a count for 1 millisecond. So let me create the function void, for example, delay millisecond. We'll call it millis, easier. And as usual, I have some typo issue. Good, void. And after that, good. So now our Systick is ready, but we need to change the load that we have. So for the Systick load now, what we need to have, okay, so the Systick here, I need to have 70, how much we said, just a moment. If I go back to debug mode and I run here and I check my power, so I have a 72 megahertz clock speed. So if I would like to have 1 millisecond, I will need to have 62,000 for each load. Okay, so I put the load here, and then equal 72,000 minus 1. And this is because if I put only 72,000, it will be plus 1 cycle. And then I put Systick current Systick value equals 0. This is to initialize my my value for the load, and I put 0. Finally, let's go back here. So we have to keep running, and when the load value goes to 0, then my counter here will have 1. So I will put a while, and I'll be waiting until my flag is getting 1. Okay, so what I have to put is while. Okay, and so while Systick. So let's open another 2 brackets, Systick and Systick and control, and let's try to put the right zeros, 0 0 0 1 and then 0 0 0 0. Let's confirm here is the right. So I have here 4 zeros, which is the right one, and then looks pretty good. Great. Equal 0. So when we start having that one equal 0, so if this one is equal 0, then we already finished the loop and we can leave it. Great. So this function should run for 1 millisecond. So for 1 millisecond, I'll be waiting until we have this flag. Good. So actually, so I just to avoid any confusion. So when this current value, when the current value will become 0, this flag will become 1. And since it's not 1 and it's 0, we're still inside this loop. Good. So the last function, which is a void also, but delay, let's put a D, delay ms here, and we can insert unsigned long t, and this is the number of millisecond that I would be asking for my program. So for, I don't need to put this, t greater than 0, t minus minus, okay, I just put here the function delay millisecond. So I'll be repeating this function. Okay, good. So this one I forgot to put the brackets. Finish the last bracket. Okay, perfect. Good. Let's confirm again the numbers are correct. Okay, so far looks good. Great. So now let me add this function here on the top. Here. And also this function. And now let's replace the delay function that we used to have, this one, like this. But this is 10 milliseconds, that's quite very short. I put 1000, which is 1 second, here and here, just to see how things would be going on. Okay, looks good. So let's rebuild and load in the microcontroller. Okay, and let's have a check in real life situation. Okay, so it looks that the system now is working and we do have a blinking LED. So let's check how much time it's taking. So let me try. I'll try to catch up with blinking one when it starts. So we do have a lag and we do have 2 seconds. So let's confirm. Oh, okay, because yeah, I wrote the program and I lost a little bit myself. So I do have 1 second wait, and then it goes and waits another second. So now I have 2.2 seconds. Just to let you know that like the clicking speed is quite making a bit gap. Let's try another one. Okay, it's from 1.9 to 3.9, so it's almost 2 seconds, which shows that with this new Systick timer, we can control exactly how much time we can do an operation, or by how much time we can make an operation happening. So this is great. So now we do have something we can use to measure the time. The next video will be more about how to use the Systick to generate interrupts and to have interrupts happening to a certain time. Thank you a lot. I added also the code in the GitHub link that you can find below the video. If you enjoy this video, please subscribe. Thank you and see you soon. Bye.